Section 5.3, Supported Vector Machine. The algorithm was developed in 1995 by Cortes and Vamnik. It can be considered as an extension of the perceptron and add line. The key additional operation is to maximize the margin. Let's look at this picture. When you are using perceptron or add line, then the resulting model, resulting separator can be one of these. For example, if it is the vertical separator, and if we have new data point here, then the model will recognize as one of the plus points. However, we can easily see that this must be one of these, so that this means that along with that separator, in generalization, the accuracy is very low. In fact, such separator can be considered as an overfitting. Now, in SVM, we try to construct a separator such that if we try to make a band, then the margin, the bandwidth is as large as possible. That's the main idea of the supported vector machine. Now, to formulate the idea into a mathematical equation, we start with here boundary, the hyperplanes. Okay, now that one is now the hyperplane, so that the net input is 1. This one, the other side, and that hyperplane is now negative hyperplane, so that the net input is -1. So here, the center one will be 0 here, net input. So in this way, we start with boundary hyperplanes, and we write down here the equation, including the bias. Then if we subtract these two equations, then we can reach at this one, right? Now, x plus and x minus is one of the points from positive side and from negative side. For example, it can be now this point and that point here. That is x minus. That can be now x plus. Okay. Okay. So we have this equation. Now, if we divide by W norm, then we have this equation. Now we have to interpret this term. Okay. Here, and x plus minus x minus is the vector, and W over W norm is now, okay, length 1 of W vector, normalize the weight vector. When you make a plane, then along with that equation, hyperplane, then W is a normal vector. We'll see sooner or later that W must be normal vector. So once it is normalized, then now from the formula, you can write down this one, this norm, and that is here 1 times the norm of that one, x plus minus x minus, and now times cosine theta, the angle between this vector and that one. Now here pictorially we can express it that one. Now W in normal direction is this one. Now here the length times cosine theta will be exactly this length. So that term is now indicating the margin, the width of the margin. So here we want to maximize this term. That means now we have to minimize W. Okay, so here the linear SVM is formulated in this way. We try to minimize W, and of course over there, when we are using W notation, then also it is including now sometimes we are using that one without including W0, but when we try to make that one, then in fact now W is expanded so that here that W is same as now vector including W0 in the beginning and W1 to W, okay, that is D dimension. Then we have that. Sometimes we are using that one as W, but sometimes we are including that one. But from the expression, you can understand what it is. Anyway, here we try to minimize the W norm squared subject to the constraint. Once yi, the label of xi's point is 1, then it's larger than or equal to 1. And the net input is larger than or equal to 1. And if it is -1, so that the one of a negative data set, then now net input must be less than or equal to -1. So we have to solve that problem. Okay, here the W is a normal vector to the distance boundary. And okay, so that portion you have to solve it from exercise for the exercise of 5.1. Now I'll try to give you a little bit of a hint. Okay, now there is a hyperplane, and if you choose one point, then you can make for instance a normal vector, for example like W. Then now for any x over there, and if you are making, okay, that is x0, so that if you try to make a dot product along with that vector and x minus x0 and W, then it will be 0, so that x minus x0, oops, here. Okay, now there is x minus x0, and now dot W must be 0. That implies that here, okay, that is now x dot W and minus here x dot W equals 0. So that this portion is the same as W transpose X, and if we are defining this portion as W0, then now it's 0. So that for any constant here, in fact, the W, that is normal vector of the hyperplane. Right? Once you start with that one, then you can get this one. But the other way also you can prove that you may start with this one and then you can figure out that is a normal vector. Okay? Okay. Now that's the objective function for the linear supported vector machine. These two conditions can be written in this way. Now we are moving this one, okay. Once we try to multiply here yi, so that it can be either 1 or -1. So that once it is yi, then if it is 1, then not changing. Once it is minus 1, then for that one, now yr is multiply, then this portion must be larger than or equal to 1, so that eventually we can read I for these two inequalities into this one unified inequality. So rather than this one, we may try to use that inequality as the constraint for this optimization problem. Now, the SVM, linear SVM, is quite well working for linearly separable data set. However, once it's not separable, then here the method may not classify correctly. So it can have a large error for inseparable data set. We have to, so that we have to adjust, we have to expand the original, the algorithm to classify noisy data sets, okay? And now for this problem, this constraint to optimization, we have to use the method of Lagrange multipliers. So in the second part, we'll consider the method of Lagrange multipliers. Thank you.